Today, we're going to explore how we can teach a computer to understand the meaning behind words. We'll be looking at a technique called word-to-vec, which is all about learning the subtle relationships in human language.
So let's start with a simple question. How does a computer know that saying scale your business and grow your business means basically the same thing? After all, computers don't understand words, they only understand numbers. By the end of this, you'll understand exactly how we bridge that gap. The old way of representing words was to treat each one as a completely isolated point. It's like saying grow and scale have absolutely nothing in common. The new way, using what we call word embeddings, is totally different. It gives each word a set of coordinates, placing it in a sort of meaning space. Suddenly, words like grow and scale can become neighbors. To really appreciate this shift, let's first take a quick look at the problem word-to-vec was actually designed to solve.
This old method is called one-hot encoding. Basically, if your vocabulary has 10,000 words, then each word is represented by a list of 10,000 numbers. It's all zeros except for a single one at that word's unique position. This means the computer sees cat as being just as different from dog as it is from Rome. There's no concept of similarity, and it's incredibly inefficient.
So how do we fix this? Well, the key insight is actually surprisingly simple, and it comes from a long-standing idea in linguistics.
And here it is. This is the principle that changes everything. It's the simple observation that you shall know a word by the company it keeps. If two different words tend to appear surrounded by the same neighboring words, they probably have very similar meanings.
This leads us to the big idea. What if we could build a map of meaning? Think of it just like a geographical map, but instead of plotting cities, we're plotting words. The crucial part is that the distance between any two words on this map tells you how similar they are in meaning. What's really powerful about this map is that you can do math with these coordinates. For example, the direction and distance to get from the word king to man is almost identical to the path from queen to woman. This map doesn't just store similarity, it actually captures relationships. Now, just keep in mind, this isn't a map you can draw on a piece of paper. To capture all the complex nuances of language, these word maps typically have anywhere from 50 to 500 dimensions. So how is this map built? Well, you start by feeding a huge amount of text, say all of Wikipedia, to a neural network. The network has a simple job: get good at predicting a word based on its neighbors. As it trains, it's constantly adjusting the coordinates for every single word. Over time, words that show up in similar contexts get nudged closer and closer together on the map. Okay, so that's the core intuition. Now let's look at the specific technique that puts this idea into practice. That technique is word-to-vec. It was developed by a team at Google back in 2013, and it was a breakthrough because it gave us a really efficient way to build these maps of meaning from enormous data sets. Word-to-vec actually comes in two main flavors. The first, called Continuous Bag of Words, or CBOW, is like a fill-in-the-blank puzzle. It looks at the surrounding words and tries to predict the one in the middle. The other, skipgram, does the exact opposite. It takes one word and tries to predict its neighbors. CBOW is generally faster, but skipgram often does a better job with rare words. Now, word-to-vec isn't perfect, of course. Its biggest blind spot is with words that have multiple meanings, like the word bank. Word-to-vec just creates a single coordinate for bank, which ends up being a weird average of a riverbank and a financial bank. It also treats words as single units, so it doesn't know that run and running are related. So this technique is over a decade old. Why should you still care about it today? Well, because these vector maps are still fundamental to a lot of technology we use every day. They power smarter search engines, they help with product recommendations, and they're a key component in everything from machine translation to sentiment analysis. And this really gets to the core of it. Even with more advanced models out there, word-to-vec is still so relevant because it's fast, it's cheap to run, and it provides a really solid baseline for almost any task involving language. So, to put it all together, word-to-vec is a technique that transforms words into numerical vectors, which lets machines finally understand meaning based on context. If you remember just one thing, make it this. A word is known by the company it keeps. That is the simple, powerful idea behind all of this. And I'll leave you with a final question to think about. If something as messy and complex as human language can be mapped into a geometric space, what other human concepts could be mapped in the same way?